do it this way.
Alright.
Hi, I'm Brian McEwen, and behind the camera right there is Ethan Luo, and we'll be demoing our Lab 2, the 82 DAC lab for CSCE 462. I'm going to start with a hardware demo. So here we have our Raspberry Pi. It's connected to the computer, ribbon cable to the breadboard, and on the breadboard we have a button connected to a GPIO pin so that we can signal to the code when we're going to put an input in for the waveforms. We have the DAC chip that is connected to the serial data line and the serial clock line for I2C communication, and it has its ground line connected, and it has the V out connected to the 82 so that we can manipulate the voltage to show the waves on the waveforms software. And lastly, we have a resistor connected to ground here. Now Ethan will be doing the software demo.
Okay, so our code is relatively simple. So we basically just have our button callback, which is basically just when we press the button, we'll have this function call. It'll ask for the shape, frequency, and voltage, and then depending on which shape they shows, we'll either call the square, sine, or triangle function. And we have this while true to keep the program running the whole time. And yeah, so if we look at our square, basically we calculate the period using 1 over the frequency, and then we sleep for depending on how long, and then we set it to either the raw value to be either the voltage that we have at most, or we set it to 0. That's how we get the square wave. And for the sine wave, we basically just call the internal sine, but we just generate points in the range from 0 to 200, and basically that gives us 200 points to display, and we're currently just displaying them as fast as we can using a while true, and basically we're not even sleeping at all. This is to get our frequency to show up as quick as possible, and it still isn't perfect even with this, but we did our best. And similarly for the triangle, we pre-compute the values that it would have to be, and we just do a while true on that. And we also do GPIO.input button. This just helps us, so if we press the button again, then it'll be able to ask for input again. So now we can show the thing actually running.
I'll demo the button right here.
So we first stop, and then let's click run. And then nothing's happening right now. If you look on the waveforms, nothing's actually happening. It's stuck at 0.
Now here I will press the button.
And first we'll demo the square wave. So we type square, and then ask for a frequency. We're going to pick 20, and then maximum output voltage we'll pick 5. So as we can see, here's the square wave, and the frequency on the right, it shows us that it's actually 20.
And now press
the button again. Okay, and now let's pick a new shape. This time we're going to pick triangle.
Here, show them waveforms before.
Oh, yeah. So
Yeah.
waveform stopped again.
Yeah.
And then now we typing triangle. And now we want a frequency of 20 again. And then maximum voltage of 5. And as you can see, here are our triangle waves. And once again, the frequency on the right here is actually 20. Okay. And then now we can press the button again.
Yeah.
Okay. As you see, once you press the button, it stops and asks for the input. So this time we'll try sine, and then 20, and then 5 again. So once again, we have our sine wave, and this is as smooth as we could get it. But the frequency does match, and it is 20.
Here, let's just demo it with 5 real quick. Or sine wave with 5.
Wait, what? Oh, okay, yeah. Now we'll demo sine wave with 5. So let's type sine, frequency 5.
This will just help better visualize the difference
Okay,
between the sine function and the triangle function. See, much more smooth.
Yeah.
All right, now we'll move on to the questions. Let's pull them up right here. Here, stop it. And then just go to my mail. All right. First is here. I'll turn it camera around. So there. All right. So the first question is there a limit to the type of function you could implement with this method? Yes, there is. It needs to be a continuous, non-negative, bounded function. So say there was a vertical asymptote, you can't approach infinity, and you definitely can't approach negative infinity because you can't have negative voltage, and additionally you can't have any holes in your function. So it just needs to be continuous, but otherwise you should be able to, with, say, you could have approaching infinite power, but
Yeah. But I think it should be bounded around like 5 for us because
for us, it would be bounded at 5.
because of the Raspberry Pi. Yeah.
Then how does I2C work, and how does the rate of communication affect your code? I2C is a communication protocol that uses the SDA, the serial data line, and the SCL, the serial clock line, and that's basically a master-slave dynamic between the Raspberry Pi and the DAC circuit, where it's communicating the data based off of the clock on the Raspberry Pi, and it's controlling the data input and output, or data flowing through the DAC, and then the DAC is then able to take that and put it into the analog device.
Okay. Yeah. And for the last one, so basically, we're given that we have 40 hertz communication. We're assuming that this means that we can do approximately, we can get 40 bits in approximately 1 second. So now that it says we have a packet of size 4 bits, that means we can do 10 packets per second. And then finally, it tells us that there's 10 points per period. So that means we can do approximately 1 period for every second. And so that gives us a maximum speed of 1 hertz for our final waveform.
I also forgot to say how it affects the rate of communication. The rate of communication would just allow the waves to be smoothed out, and because it would just be relaying more data back and forth, allowing the data points to become closer and closer.
Yeah, I think, the main thing was when it was calling the raw output, when it was changing the raw output voltage, it was doing that relatively slowly, so then it couldn't get as smooth of a function as we would hope for.
All right. Thank you, Thomas.